This first image is the original design for the control theory of the multiplier. As you can see, there's been some changes made to the original design. Here I have allowed for 0 inputs by adding 2 OR gates and an AND gate. The output of the AND gate is connected to the 0 input down at the OR gate. This goes into the last D-type flip-flop and will trigger answer good if a 0 is input. Here we have the output waveform showing the states. Here is clear sum, count sum, load sum. Load sum will continue through the next 3 states until the correct answer is found. Answer good will then trigger high, which is state 7. This shows the original state diagram along with the 1-hot code. Here's the 1-hot code. As you can see, first state is clear sum. Second state, the numbers are loaded. They are then loaded into the multiplier and load sum again. Count up. This is then looped around until equals is high, which triggers answer good. Here we have the updated state diagram to allow for the 0 input. The 0 input is a decision diamond added in below the load num. If 0 input is high, it is looped straight to answer good. This changes the 1-hot code. Here I have included the 1-hot code. State 0 is equal to S0 and not S, or state 7 and S. State 1 is equal to S0 and S. State 2 is equal to S1. State 3 is equal to S2 and not 0, or state 6 and not equals and not 0. State 4 is equal to state 3. State 5 is equal to state 4. State 6 is equal to state 5. State 7 is equal to state 6 and EQ, or state 7 and not S, or 0. Here I'm showing an output waveform to prove the control theory works. The numbers are loaded in. The count continues to count until the correct answer is found. Answer good will then go high when EQ is also high. Here I am showing the control theory changed into a block. The block has then been added to another design to allow for the multiplier to work. This is the original multiplier, which only had to deal with 4-bit numbers. Key part of this is the 0 input. This is to detect when a 0 is input into the design. It is a simple design, and this is it's shown. It is for the this is for the 8-bit number. There are 8 inputs into a NOR gate, sorry, which is then connected to 0 output. The multiplier is then changed into a block. The block has been added to a design. Here we have 8 switches where I can choose an 8-bit number to be input into the design. The two 8-bit numbers are input at PB0 and PB1. PB0 and PB1 are connected to LPM latches. They are latched into an 8-bit register. The multiplier will multiply the two numbers and give a high signal at answer good when the correct answer is found. The output of the multiplier is fed into two 7-segment display decoders, also fed into 8 LEDs to show the output. The 7-segment display decoders had to be programmed using VHDL code. This is the VHDL code used for the 7-segment display. However, there is a problem here. The 7-segment display is actually triggered low. So when 000 input is put in, the output should be 10000000. This will give an output of 0 shown. This will light up segments A, B, C, D, E and F. After I had corrected the VHDL code, I then had to assign the pins. This is to program an IC to allow the output to show on a 7-segment display and to allow you to input the numbers manually. Here's the output waveform for my final 8-bit multiplier. Here are the two numbers input, the clock signal and the count, and also good. Here I am showing what is shown on the 7-segment display. Multiplication was 8 multiplied by 8, which should give a hexadecimal output of 40. Here is my output. It is not very clear here, however the output did show 40.